Right now, inside every major commercial building in New York City, a system runs that most people never see or think about until something fails. Tight shot of a mechanical penthouse. Exhaust fans turn, condensers hum, pipes and ductwork frame the roofline. The camera tilts down the glass facade, floor after floor of lit offices. Photorealistic, cool tones with warm window light. Cut to a dim control room. An operator at a curved workstation studies multiple monitors showing floor plans, system diagrams, and live data. No dialogue, just focused presence. A red alarm banner flashes. AHU07, supply air temp high, 74 degrees Fahrenheit. The operator moves the mouse. Tension. It's called a building management system. For anyone in facilities, engineering, or operations, understanding it isn't optional. It's the foundation of everything you do. A building management system, or BMS, is the integrated control and monitoring network for buildings' mechanical, electrical, and sometimes life safety systems. Think of it as the building's nervous system. Every sensor, motor, valve, and fan is connected, monitored, and controlled through one platform. The BMS reads field data, executes programmed logic, and sends commands back to equipment, in real time, continuously, whether anyone's at the workstation or not. What does the BMS read? Inputs from sensors. Temperature sensors in ducts, intakes, pipes, and occupied spaces. Pressure sensors for duct static and filter differential. Humidity sensors for sensitive spaces. Electrical meters reporting kilowatts and demand. And flow meters for chilled and hot water. These points show how air, water, and power are behaving. When a filter loads and differential rises, or demand spikes on a meter, the BMS sees it first, feeding operators data used for energy programs and fault detection. Outputs are where the BMS acts. Damper actuators modulate outside and zone air. Valve actuators throttle chilled and hot water to match space loads. Variable frequency drives, VFDs, adjust fan and pump speeds so motors run at the required speed, saving significant energy compared to running at full speed. A supply fan at 60% can use far less power than at 100%. Together, these inputs and outputs form closed loops. The building reports conditions, the BMS responds, the building stabilizes, and the cycle repeats continuously. Not all BMS platforms look the same. In New York City, you'll often see Siemens, widely deployed with robust graphics. Johnson Controls Metasys, common in healthcare and large mixed-use projects. Distech Controls, favored for flexible open protocols. Automated Logic Web Control, web-based, popular in education and mid-size buildings. And Skyline, valued in certain institutional markets for customizable graphics and alarm handling. Each platform offers a graphical front end, alarm management, scheduling, and trending, just with different strengths and interfaces. Every platform shares the same core architecture, a graphical front end to visualize systems in real time, an alarm engine to generate, log, and route faults, a scheduling module to automate equipment around occupancy, and a trending database that stores historical point data for analysis and troubleshooting. Knowing how to navigate a platform, pulling graphics, reading values, acknowledging alarms, checking schedules, and pulling trends is the baseline. A strong operator goes further. They verify the screen against the field. If the BMS says supply air is 55 degrees Fahrenheit, a strong operator measures discharge with a calibrated thermometer. If the BMS shows a valve at 80% open, they check the actuator position on the valve body. Sensors drift, actuators fail, wiring corrodes. A system can show stable graphics while the building quietly underperforms. Field verification is how you catch it. The BMS is the most powerful tool an operator has, but it's only as reliable as the person using it. Learn the system, learn the equipment, and trust your hands as much as your screen. That combination is what makes a strong operator.